Okay, here we're doing some more analysis on logarithmic functions. So consider the function log base 2 of x. So in the background, I'm going to be thinking of y equals 2 to the x because that's one I'm a bit more comfortable with. We learned it earlier on, and so I can do domains and ranges by thinking of the flipping of the y's and the x's, right? So domain, the domain is the same as the range of y equals 2 to the x. And I know y equals 2 to the x looks like this. So for this domain, the domain is going to be the range of that graph, which is 0 to infinity. And then the range of the logarithm function is going to be the same as the domain of the 2 to the x. So it's negative infinity to infinity. The more mathematically mature you become, the less you think of y equals 2 to the x, and the more you start thinking of what y equals log base 2 of x actually itself looks like. Because then you can see that its range is negative infinity to infinity, and its domain is only positives from 0 to infinity. Okay, next part of the problem asks us to determine the coordinates of at least 5 points on the graph that will fit in this grid. And so the grid is restricting us between only up until 8 or so. So let's go to the highest possible number we can, then we'll work backwards. Let's go with 8. Because notice that I can tell you what log base 2 of 8 is. Log base 2 of 8 is what exponent do I put on 2 that gives me 8. So of course that would be the number 3. Now I won't do 7 or 6 or 5, but instead I'll jump to 4, because what exponent do you put on 2 that gives you 4? That's squared. What exponent do you put on 2 that gives you 2? That's 1. What exponent do you put on 2 that yields 1? That's 0. And then it does command 5 points, so I'll have to go a little bit further and think, well, what is the exponent that I can put on 2 that will give me the reciprocal, which is 1/2, and that's negative 1. So notice over here we have that same relationship, almost going back to exponential, but inverted because logarithm's inverted. 3, 2, 1, 0, negative 1. These are changing by 1s. And divide 2, divide 2, divide 2. These are changing by dividing by 2. Okay, so 8, 3, 4, 2, 2, 1, 1, 0, 1/2, negative 1. My graph seems to be acting like this. It has an asymptote located here, and the equation of that asymptote is the vertical line x equals 0, also referred to as the y-axis. So again, notice how we're not shocked here, right? If we get better at math, we start to see this kind of graph as our parent function when we're doing analysis. So when I do everything over here, I'm not terribly shocked by how the picture turned out. Okay, next problem is similar, except now we're doing a log base 1/2 of x. So again, our domain is going to be 0 to infinity, because those are the numbers that are legal for logarithms. My range is going to be negative infinity to infinity. But this time, because I'm doing things to the 1/2, when I have a base of 1/2, I'm going to choose my numbers a little differently over here. What power do I put on 1/2 that gives me 1/8? That's 3. What power do I put on 1/2 that gives me 1/4? 2. What power do I put on 1/2 that gives me 1/2? 1. What power do I put on 1/2 that gives me 1? Well, 0, because anything to the 0, any number bigger than 1 or bigger than 0 raised to the 0 gives you 1. And then finally, my awkward number is going to be 2, because then I have to reciprocal the 1/2, and that's going to give me negative 1. So those points would look like, let's see, 1/8, 3, 1/4, 2, 1/2, 1, 1, 0, 2, negative 1. So we can see what's happened here is a reflection that seems to have occurred over the x-axis, right? It's kind of flipped over here, and that's something to do with the powers there. We still have the same asymptote. The asymptote is at x equals 0, and that completes the graph of the log base 1/2 of x. Okay, so now here is a summary of that information in a convenient place, is that the graph of the exponential function gives you 0, 1, 1, a, and -1, the reciprocal of a. So when you reverse the x and the y's, that means that you'll end up getting log base a of x gives you 1, 0, a, 1, and reciprocal of a, -1, right? They literally invert each other. And again, like we've mentioned before, we can imagine the analysis here. We can imagine this graph flipping over y equals x to yield this graph because they're inverses of each other. So remember that a, be careful when the value of a is between 0 and 1, because even though it includes the same points, that graph will end up looking like that awkward graph we saw before. It has some flippiness that's happened due to the powers. So that's all that this note is making you to be aware of. This graph, this standard shape, will be for any a's bigger than 1. Okay, summarize up the properties then. The domain of a log base a of x is always, for all the a's that are valid, a is bigger than 0 but not equal to 1, a bigger than 0, a not equal to 1. The domain will always be 0 to infinity. The range will always be -infinity to infinity. The x-intercept will always be located at 1, 0, and the y-intercept doesn't exist because the vertical asymptote is x equals 0, also known as the y-axis. So you never actually do hit the y-axis. There is no actual y-intercept. The log base a function, as you can see, is going to be an increasing function as long as a is bigger than 0. But then, as we saw in that example, if we end up taking numbers that are between 0 and 1, like 1/2, our function now decreases. So if 0 is between, or a is between 0 and 1, it's going to be a decreasing function. Every log base a graph will always contain the same 3 standard points, the 1, 0, the a, 1, and the 1 over a, -1. And it'll be smooth, and you never have to lift the pencil off the paper. There's no corners, there's no gaps. It's a nice, simple function, nice, simple shape. Okay, so let's use that to graph a couple of these parent functions then, or graph a couple of these transformations on functions. Log base 3 of x would normally have a handful of pretty points, right? The handful of pretty points would be 1, 0, and then you'd have a 3, 1, and then you'd have a 1/3 with a -1. However, here we have a doubling, a vertical stretch factor, and we have a shift left 1. So 3, 1 is right here. Double it becomes 3, 2, shift left 1. 1, 0, doubled would still be 1, 0, because the y value doubled is still 0. Shift left 1. And then maybe the semi-awkward one, 1/3 with an output of -1 is going to be right here. But then doubled means instead of being -1, it's going to be -2, and then it's going to get shifted left 1, so instead of being at 1/3, it's going to be at -2/3. So our graph will generally, with those 3 points at least, look something like that. Notice its asymptote is no longer at x equals 0. Its asymptote is now at x equals -1. Similarly over here, this is the log base 3 of x graph, same parent graph, but now shift up 2. So 3, 1, up 2 becomes 3, 3. 1, 0, up 2 becomes 1, 2. And a 3rd, -1 shifted up 2 becomes a 3rd, +1. So there is our graph. There's our graph this time. This time the asymptote is still at x equals 0 because a vertical shift does not affect a vertical line, right? Shifting this line up and down keeps it in the same spot. Okay, now we get to formally define what I called ln in a previous lesson. So when we have these logarithms, we can take logarithm in whatever base we want. We have two very, very special bases. One of those very, very special bases is e. So when we do log with a base of that special e number, that 2.17 or 2.718-ish number, we will use a abbreviation of using ln for the log au natural. Actually, I think it's due to Napier. It's Napier's log. This button is on your calculator right here, and it's associated with, if you look above it, you can see there's an e to the x here. So that's how you can remember ln and e to the x are married. So if you want to do the ln of e, the log base e of e, what number do I have to raise e to in order to get e? Should be clearly 1, but let's calculate it. ln of e, remember the e is located here above the division, that gives you 1. What exponent do you raise e to in order to get e to the 5th? Well, that's literally 5. What do you raise any number to in order to get 1? That's 0. And what do you raise e to in order to get a reciprocal? That's a -1. So that is how we work with the natural logarithm, log base e. The other special base we really like is common log, or log base 10, so named because of our 10 digits, right, our 10 fingers, essentially. So these would be, if these are so important to us, log base 10, that it's kind of a default when we write down a logarithm in which we don't write a base, you are paid to assume that that base is 10. So notice here we don't have a base, and that means this base is 10, and so the question is asking, what power do you put on 10 to give you 1,000? Our calculator has this button located right here at the log, log base 10, and you can remember that because right above it, it does say 10 to the x. So what is log of 1,000? What power do you put on 10 to give you 1,000? Hopefully you already guessed that that's going to be 3, right? Because you have to raise 10 cubed to get 1,000. So this is 3. What do you raise 10 to in order to get 10? That's 1. What do you raise anything to get 1? That's 0. And here we want 100, which would be 10 squared, but reciprocal. So that answer is going to be a -2. So again, log with no number as a base is understood to be base 10. And ln is understood to be a logarithm base that nice fancy number e. Okay, so now how do we go about solving logarithmic equations? Remember that the arguments, because the domain for logarithm can never be negative, so we're going to have to do these and make sure that we don't have any negative answers, so sometimes we'll get extraneous solutions. How do we undo log base 6? We raise 6 to the power of both sides. This will cancel out 6 and log base 6. So x minus 2 equals 6 squared, which is 36. X equals 38. And quick check, 38 minus 2 is positive. It's 36, so this is a legal answer. A-OK. Log base 3 of x squared minus 2x equals 1. Raise 3 to the on both sides for the cancellation. So we get x squared minus 2x equals 3 to the power of 1. Subtract 3 from both sides. Factor x minus 3, x plus 1. So x equals either 3 or -1. Let's check to make sure they're legal. So if we were to replace 3 for x, 3 squared is 9. 9 minus 2 times 3, 9 minus 6 is 3. That's positive. Legal. -1, -1 squared is 1. And 1 minus 2 times -1, that's also 3. So that one's legal. So it's not that negative numbers are not allowed. It's that when you replace the negative numbers in here, you need to make sure that the argument is positive. Okay, this one. How do we undo? Well, first of all, let's get the logarithm by itself. Divide by 3 so that ln of 4x equals 9. How do we undo natural log? That's the e as the base, so that we get 4x equals e to the 9th, and then divide by 4. So e to the 9th over 4, box, happy face. That's definitely a positive number, so this one's totally fine, completely legal. Last problem then, let's isolate first by subtracting 7, so that 9 log x equals negative 3, and then divide by 9, log base x equals negative 1/3. Cancel out the common log. Remember, there's no base here, so this is understood to be base 10. So I'll raise 10 to the on both sides, so that I get x equals 10 to the power of negative 1/3. Box, happy face. For these problems, it asks us to rewrite an exponential equation in log form and then find the exact solution. So to rewrite this one in a logarithmic form, this is an e to the 3x. So what's our logarithm for a base e? That's ln. ln log base e of 7 equals 3x. Right? That would be the logarithmic form of this. Log base e of 7 equals 3x. So to isolate x, we'll just divide by 3 and conclude that x equals log 7 over 3. Over here, we need to undo 10 to the. So to undo 10 to the, we'll do a log of both sides. Log of both sides, another way of looking at it. And then the log and the 10 to the cancel each other out, bringing the base down. And so to isolate x, we would add 1 to both sides. Log 9 plus 1. Again, I'll put those extra parentheses around here just to make it super clear that I am not plussing 1 to the 9. It's a plus 1 after I have done log of 9. Okay. Hey, and that's it for today.